Hey there, welcome back to my channel. Today, we are going to explore the fascinating world of digital electronics and computer architecture, specifically the 41 multiplexer and adders. Let's begin with the multiplexer. Have you ever wondered how a single output can be chosen from multiple inputs in digital circuits? A real-life application is pressing different buttons on the TV remote, but it selects a specific channel displayed on the TV. Isn't that concerning? At the end of this presentation, we will understand how this real-life application works. First of all, what is a multiplexer? A multiplexer, or MUX for short, is a digital circuit that selects one of several input signals and forwards it into a single output line. Think of it like a switch that connects one of multiple inputs to a single output. Now, let's take a closer look at our 4-to-1 multiplexer circuit. We have 4 input lines labeled I0 to I3 and 2 select lines labeled X0 and X1. The circuit consists of 4 AND gates, 2 NOT gates, and 1 OR gate. The select lines X0 and X1 receive a binary code that corresponds to the desired input line. The multiplexer decodes the select lines and enables the corresponding input line. The enabled input line is then connected to the output line. The output line carries the selected input signal. So simple. How does it work? Or how it works? An X1 and X0, the multiplexer selects input line I0 and connects it to the output line. And when X1 is equal to 0 and X0 is equal to 1, the multiplexer selects input line I1 and connects it to the output line. When X1 is equal to 1 and X0 is equal to 0, the multiplexer selects input line I2 and connects it to the output line. When X is 1 and X is 0, when X1 is equal to 1 and X0 is equal to 1, the multiplexer selects input line I3 and connects it to the output line. Now, I will take you through the importance of the AND gates in the diagram. The AND gates in the circuit are used to enable or disable the input lines based on the select lines. For example, the top AND gate is enabled only when X1 is equal to 0 and X0 is equal to 0, allowing the signal from I0 to pass through the output line. Also, the OR gate is used to combine the outputs of the AND gate. It produces an output only when one of the AND gates is enabled. So, in summary, the 4-to-1 multiplexer works by using the select lines to enable one of the 4 input lines and connect it to the output line. The AND gates and OR gates are used to implement this logic. Now, we'll proceed with adders. This image clearly illustrates the fundamental building blocks, half adders and full adders, and how they combine to form a ripple carry adder. The core function of an adder is to perform binary addition. Let's look at the half adder. Look at the top left of the image labeled half adders. What's its purpose? A half adder is the simplest form of an adder. It takes two single binary inputs, A and B, and produces two outputs, a sum and a carry. Also, the logic gates, XOR gate. This gate produces the sum. The output of a XOR gate is 1 only if its inputs are different. So 0 plus 0 is equal to 0, and that's the sum. And also 0 plus 1 is equal to 1, and that's a sum. Also 1 plus 0 is equal to 1, and also 1 plus 1 is equal to 0. That's the sum, because 1 plus 1 in binary is 10. So the sum is 0 and the carry is 1. The AND gate. This gate produces the carry. The output of an AND gate is only 1 if both of its inputs are 1. So when you look at its output, 0 plus 0 is equal to carry 0, and 0 plus 1 is equal to carry 0. 1 plus 0 is equal to carry 0, but 1 plus 1 is equal to what? Carry 1. You can see this from the above diagram. Let's look at its limitations. A half adder cannot handle a carry in from a previous addition stage. This is why we need a full adders for multi-bit addition. So let's look at the function or the importance of a full adder. Now, look at the middle and the bottom sections of the image labeled full adders. What's its purpose? A full adder takes three binary inputs, two data bits, which is A and B, and a carry in from a previous stage. It produces two outputs, a sum and a carry out. The logic gates behind this can be seen in the image. So the image shows that a full adder can be constructed using two half adders or an OR gate. The first half adder takes inputs A and B, producing an intermediate sum and carry, which is S1 and C1 respectively. The second half adder takes the intermediate sum and the carry in, which is the S1 and the C in, producing the final sum X and an intermediate carry C2. An OR gate combines the two intermediate carries C1 and C2 to produce the final carry output, which is the C out. This is because a carry is generated if either A and B are both 1, or if 1 of A over B or divided by B is 1 and there is a carry in. Why is it full? The ability to incorporate a carry in makes it suitable for adding multiple bits, as the carry from one bit position can be propagated to the next. Let's look at the ripple carry adder. Finally, consider how multiple full adders are chained together, as suggested by the ripple carry output connection on the right. You can view this on the image above. What's its purpose? Its purpose is to add binary numbers with more than one bit. Example, the 4-bit, 8-bit, 16-bit numbers. We use multiple full adders connected in a ripple carry configuration. How does it work? The least significant bits of two numbers are fed into the first full adder, along with an initial carry-in, which is usually 0 for the first stage. The carry-out from the first full adder becomes the carry-in for the second full adder, which adds the next pair of bits. This rippling of the carry continues from one stage to the next, from the LSB to the most significant bit, MSB. The final outputs are the sum bits from each full adder and the final carry-out from the most significant stage. In summary, using your chosen image, you see the basic XOR and AND gates forming the half adders from initial sum and carry calculations. These half adders are then combined with OR gates to construct the more comprehensive full adders, which can accept a carry from a previous bit position. Though not explicitly drawn as a chain in this specific image, the ripple carry label on the presence of distinct full adder blocks imply that you would connect the carry-out of one full adder to the carry-in of the next to perform multi-bit binary addition. The carries ripple through the circuit, affecting the sum of subsequent bits. However, others perform binary arithmetic addition, while multiplexer, specifically a 4-to-1 max, acts as data selector or routers. Their primary relationship is that a multiplexer can be used to select the output of an adder as part of a larger system, like an arithmetic logic unit, the ALU. In this scenario, the adder computes a resource and the max decides if that resource is the one to be passed on. Both are fundamental components in building complex digital circuits with adders, handling computations, and the maxes managing data flow. Thank you very much. Watch out for more videos. And this is the end of the presentation.